So hello everyone, welcome back from the full break. So I hope that everyone has a little bit rest, even though it's just 1 day or 2 days. So I'm sorry that I cannot be in the class with you guys, and so I decided to record this video. So I'm going to break Thursday's lecture into two videos. So one for the remaining part of the section 9.2 about the similarity, and the other would be the starting of chapter 10 or about circles. And so I'm after I finish the recording, I'm going to upload it to like YouTube list. So it will be like two individual videos, and I will post the link. So once you click the link, it will directly lead you to the video. And don't forget that the homework 7 is going to do this Friday, October 15th. And since we only essentially have one lecture for this week, so homework 8, I expect will not be too many problems, and it's going to be due next Thursday. So definitely please, for this Thursday, you should watch the video I recorded here and also record the lecture notes. And so I decided not to show my uh, like video or like my face because it's a little bit um, like distracting for me. So I just decided just for the audio part. So you can see me pretty soon next Tuesday. And so I will also post the lecture notes I'm using today on the Blackboard, so you can definitely use it as a reference. So last time we talked about 9.2, which is similarity. So I think I only managed to introduce the definition of two triangles to be similar. And I also did approved one of this very important tool, proposition 6.2. So later on, I'm going to use 6.2 to prove the following two triangle similarity scheme. And so we actually have three triangular similarity scheme, but I decided because the time constraint, I'm going to only prove just two of them, and the remaining one, I'm going to ask you to read the textbook as an exercise. So first of all, let's recall what's the definition for like having two triangle to be similar. So we say that two triangle ABC and DEF to be similar if first they are equiangular, meaning their angles are corresponding equal, right? So A equals D, B equals E, and C equals F. But this is not congruent anymore. So we don't have the exact same um, sides, but rather we have the sides to be in proportion. So you can see that the AB divided by DE and the ratio will equal to AC divided by DF and BC divided by EF. And we use this notation, ABC tilde DF means similar triangle. So here you should really, really be careful that when you write a proof for homework or later on for the final exam, you should distinguish the notation for similarity and congruent scheme. And later on, you're going to see that you should do the same for the triangle scheme, right? So you will see that we add a tilde on the triangle scheme to emphasize that it's a similarity scheme. So last time we talked about this 6.2, which essentially tells you that if you have this, so if you have a triangle ABC, so let me draw a picture here. And let's say you have a point D on AB, doesn't matter where it is, right? And if you have E on AC, and we actually showed, this is the proof already, we already done the proof is done before the exam. So you should go back to check your note. So we actually showed that we can actually show if DE is parallel to BC. And this is a biconditional statement. And this condition, if and only if that you have this sides in proportion. So this tells you that AD divided by DB is equal to AE divided by EC. So you can see that the sides are in proportion here. And this even only if means that this condition or statement are in both direction. So which means if you have DE parallel to BC, then this implies the sides are in proportion like this. And vice versa, if you have sides in proportion like this, then it implies DE is parallel to BC. So I remember last time, at least I did the proof for one of the direction and leave the other as exercise for you to read. So we are going to use this important tool to prove the following two triangle similarity scheme. So now let's see. So this is triangle similarity scheme. So the first one, or actually is the commonly used one. So this is proposition 6.4. Essentially, I would say just the AAA similarity scheme. And as you can see, we use this notation, delta on the top. So when you're trying to, like later on when you write down the proof, when you're trying to say this is a AAA similarity scheme, please put a delta on top of the letter to distinguish it from the triangle scheme, the congruent scheme, right? Unless you write it down explicitly that this is similarity scheme. So this 3.4 tells you, the AAA delta tells you equiangular triangles are similar. Meaning if you have, so this is essentially, I write down the modern statement. If you have two triangle ABC and DEF, and assume if the corresponding three angles are the same, then we have the sides are in proportion. So remember that the definition for two triangles to be similar means that not only you need to have the equal angles, the sides should be in proportion. So this tells you that if two triangles, if you already know that all the angles are equal here, like corresponding equiangular, then it will implies the sides will also be proportionate. Then this essentially tells you that this implies essentially in the end, because now you have the equiangular and also the proportional sides, then eventually what you said, what we obtain is that the triangle ABC is similar to DF. Right? If it's only the assumption that the three angles are corresponding equal, then this is not a similar triangle yet, right? But then we actually can prove you only need to have three angles to be equal like this. Okay, so for this one, we need to actually, the proof actually has two cases. The first case is actually the easy part. So the case one, the spatial case, right? So we want to separate into two different cases. Either the side AB equals DE, or side AB is not equal to DE. So first of all, let's say if AB is equal to DE, right? Then we have, let me draw the picture here. So this is ABC and DEF. So our assumption tells us that we already know the corresponding angles are equal, right? So now first case, what if AB is actually equal to DE? Then right away you can see that we actually have congruent triangle in this case, right? Something even stronger. So if this is the case, right? AB equals DE, then by what we know, the ASA congruent scheme, we have two triangles to be congruent. So be careful the notation here, right? So I'm using the congruent. So if they're congruent, then it's even better. Then it's definitely like similar, right? So then two triangles are congruent. First, you get congruent. The sides are proportion, right? So the triangles are similar, and the sides are in ratio 1, right? So now, because if it's congruent, then you can see that the above ratio AB over DE is going to be equal to AC over DF and equals to BC over EF, because they're exactly, the sides will exactly be the same. So the ratio is actually 1, right? So you can see that if we already have three angles to be equal, and then the case one is if one of the side AB equals DE, then we right away have two congruent triangle. But congruent triangle is something stronger, right? So they're definitely similar triangle. So this is not too interesting in the sense that it's too like too restricted, right? So now let's see case two. Case two is more general. So what if, or assume right? AB is not equal to DE, right? Then in this case, one of them, either one of them, AB or DE is larger. In this case, we can just, because we can always swap the row of ABC or DEF, right? We can swap the row of two triangles. So it really doesn't matter which one is larger. We can just pick one case. So without loss of generality, what we're going to do is we're going to assume that AB is larger, right? So assume this is the case. Okay, so let me draw another picture here. So if AB is larger than DE, right? And we still have two all the angle, corresponding angle to be equal. So let's put this condition here. Okay, so if AB is bigger than DE, then we can pick a point G on AB such that AG is equal to DE. So let me first write down the statement here, then I will draw the picture. So we construct a point G on AB such that AG is equal to DE. And if you really want to justify this, this is by one of the proposition 1.3, right? So we can do that. So pick AG here, such that this AG is equal to DE. Okay, so now let's see. Now we want to do this trick. So we draw a line starting or passing through this point G and parallel to BC. This is also doable by one of the proposition, right? So this is by proposition. The first one is by proposition 1.3. Second one is proposition 1. I'm just providing it for a reference. So now I can definitely just construct a parallel line, right? And then starting from G parallel to BC. And now one thing we actually never really like carefully justify is that when you draw such line, we know that it has to intersect AC at one point. Okay, so this is this point, let me call it H. So you can see that first of all, this is actually can be, this is one of the like the product of Hilbert's axioms, this Pasch theorem that we kind of mentioned a while ago, right? So Pasch theorem tells you if you have a line passing through a triangle like this, if this line already intersect AB at this point G, then it has to pass through either AC or BC. Okay, so you can actually check the statement, but it cannot pass through BC because we want this line to be parallel to BC, right? So then that means it has to pass through like AC. Okay, so this is essentially by Pasch theorem. Let me write it down like what I just said here. So I want to say let the intersection of this parallel line with AC to be H. And as I said, this is by Pasch theorem. This is one of the axiom that in Hilbert's axiom. Okay, so otherwise, how do you know, right? We didn't really never justify it. How do you know that this parallel line really passed through AC, right? Why not like not passing it, right? Okay, so after this, then we have, you can see that this is kind of go back to the picture of the tour proposition, the first proposition I mentioned, like the 6.2. Okay, so first of all, I need a couple more information here. So let me continue here. Now we have two parallel lines, right? Then we can use the theorem that we like a lot. So this is 1.29 proposition. We know since GH is parallel to BC, so then we have several angles that will be equal. So these two angles, AGH is equal to ABC. right? And also, we already know ABC is equal to DEF. This is by our assumption, right? We assume that three angles are equal, right? So this essentially tells you AGH is equal to DEF. Okay, and plus we have angle A is also to angle D, right? This is also by assumption. And also we construct AG to be equal to DE at the first place, right? Then now you can see that, okay, I have AG here equal to DE, and angle A equals angle D, angle G equals angle E, so we have ASA. So now we have this smaller triangle AGH is congruent to DEF by ASA skin, right? So we have smaller AGH congruent to DEF. Okay, so that's the intermediate step. So then now, because of this, right, because we have two triangle are congruent, then we have AH, the other side AH is equal to DF. Okay, so we need this later on. Okay. Now let's see. Now it's the time to use the proposition 6.2, like the previous one, right? Because we have GH parallel to BC. Then we have the triangle, the sides will be in proportion, right? So now, so since GH is parallel to BC, right? Then by the previous proposition 6.2, right, we have those sides in proportion. Okay, so let me write it down here. So this would be GB divided by AG is equal to HC divided by AH, right? So essentially we have GB over AG equals HC over AH, okay? So this is by the previous proposition. Now I want to add 1 on both sides of the equation. I want to make it common denominator. Right, so first I add 1 as AG over AG on left hand side. But right hand side, I want to add 1 as well, right? I don't want to change the equation, but I add it as AH over AH, right? Okay, so this is the trick. Okay, so now you can see that after you add this, then they're same denominator, but numerator, you have GB plus AG. That's essentially AB, right? So you combine it. So this is AB over AG on the left-hand side. Right-hand side, you have HC plus AH, right? That's essentially AC, right? So now you essentially have AB over AG equals AC over AH. Oh, sorry, AG, and then this right-hand side is AH, okay? So now let's see, but we also know that AG equals, let me circle out here. This AG is equal to DE, right? This is by construction. AH equals DF. This is by the earlier proof where we have two congruent triangle. So now I change it. So we have AB over DE equals AC over DF. And then this is part of the ratio, right, we want, right? If you go back to what we want to prove earlier, right, we want to prove that two triangle ABCDF, the sides are in proportion. And this is the first part where AB over DE is equal to AC over DF, right? So we just proved this part. Okay. So now the second half, I still need to prove AC over DF equals BC over EF, right? So second part, I'm not going to do it because it will be similar. So I'm just write it down here as a, so by similar argument. And I want to leave you to do it as exercise, right? So you probably, I can give you a hint. What you want to do is essentially, now you have DF, right, ABC. So instead of drawing a horizontal parallel line, you draw something like this, parallel line, like this, right? And trying to mimic the proof that you saw earlier. So by similar argument, we can show the second part of the proof, second part of the ratio. So once you prove this, then you have all the ratio, right? So you have AB over DE equals AC over DF equals BC over EF. Then that's how you complete the whole thing. So the second part, I'm going to leave you to do it, to mimic what we have done. But now you need to change the position of the horizontal line, right? So back then, if you go back to the proof, we draw a horizontal line parallel, sorry, we draw a line parallel to BC. Now you need to do a parallel line like parallel to AB, right? So in order to get what you want here. So that's the picture. So I'll leave you to do it as exercise, and you can try it out. If you have any question, feel free to let me know. And this is essentially AAA similarity scheme. It tells you if you know that in two triangles, if the corresponding angles are equal, then the two triangles are going to be similar. But if you think about it, technically, we don't have to know the whole three angles, right? We only need to know two. And the reason is because if two of the angles are correspondingly equal, then we already know that in Euclidean plane geometry, that the sum of the triangles are going to be 180, right? So if two of the angles are already equal, the third one should also be correspondingly equal. So actually, we have a better deal here. Instead of, most of time, instead of using AAA similarity, we only need AA. We only need two angles to be equal. So this is essentially the corollary here. So the corollary tells you that essentially you only need two angles to be equal, because we already know the third angle will have to be equal because the sum is 180. So this tells us if two triangles have two pairs of equal angles, right, then they're similar. So essentially, you don't need to have like the third one, right? So this is essentially make a highlight, like a remark here, because the angle sum is 180, right? So the third angle will definitely be equal once you have two pairs of equal angles. So you only need to have two pairs of equal angles to make two triangles to be similar. Okay, so most of the time you really don't need AAA, you only need AA, but AA delta, essentially similarity scheme. Okay, so now there's another two similarity scheme. One is SSS, but be careful, this SSS is not the same as the congruent scheme. This is a similarity scheme. So let's see what's the statement here. So it says that if you have like sides are proportional, right? Then the triangle will be equiangular and have those angles equal with the corresponding side. Okay, so first let me draw the two triangle here. So actually the statement is a little bit hard to understand. So it's better just to read the mathematics statement in the proof here. So the mathematics statement is this part that I wrote down here, right? So SSS means if you have all the sides are in like corresponding equal, have some like ratio here, then it proves that because now you have the sides are in ratio, But then in order to claim they're similar, you still need to prove that the angles are equal, right? So in this proposition, we can show if I have two triangles here is if AB over BC is equal to D over EF, and if BC over CA is equal to EF over FD, and you have the same thing for the third pair of side, then you can eventually prove that the angles has to be equal correspondingly. Okay, so you can see that the reason it's called side, side, side is because you have three, like essentially three pairs like of equal side. So that's why it's called side, 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 or like similarity scheme. So this is quite different than the usual congruence scheme. So you want to be a little bit careful here. To be honest, I think the most commonly used similarity scheme are the AA or AAA. The SSS and then later on the last one, SAS, are not that commonly used. Okay, so the proof here is a little bit tricky, so I want to actually do it here. I mean, of course, feel free to like read the textbook by yourself. So for this proposition, it tells you have these three sides are three pairs of like a ratio here, then all the angles are equal. Then essentially this implies the triangles are similar. Implies triangles are similar. Okay, right? Once you, then essentially you have the definition of similar triangles. Okay, so first of all, on probably I need to draw the picture down here. Okay, so let's keep this assumption here. So first of all, I have, let's see, so I have A, B, C. Let me draw the picture again. And I have D, E, F, smaller here. Okay, so first what I want to do is to construct a like a extra triangle here. So on EF, I'm going to construct FEG here such that FEG is equal to ABC. Okay, so I want to duplicate somehow like some kind of ABC, like an extra like triangle here. And I also construct EFG to be equal to ACB. So this is ACB. So EFG is equal to ACB, right? Then the third angle should like be equal, right? So let me do, therefore, the angle A is equal to FG. And this is because we know the sum is 180, right? Okay, so then now if you think about it, right? So let me put the last one. So so the angle A, let me use different color. So angle A here is equal to this angle G, right? So now if that's the case, you can see that triangle ABC and EFG, this extra triangle we drew, already equiangular, right? Then that means we can use AAA similarity scheme to show that they're essentially like similar. So let me do it here. So by AAA similarity scheme, right? Either you do this, right, AAA tilde, or you should say similarity scheme, right? You need to indicate it's a similarity scheme. So triangle ABC is similar to which one corresponding to which? ABC and GEF, right? G is A. Okay, yeah, in this order. Okay. So once they're similar, right? So I still don't know anything about DEF yet, right? But I create this similar triangle. So then the sides are in proportion. So this means I have AB over BC equal GE over EF, right? So once you have similar triangle, you have sides are in proportion. But at the same time, remember what's our assumption? We have the assumption where AB over BC is equal to DE over EF. So now we have the transitivity here. So let me write it down. So also by assumption, we assume AB over BC is equal to DE over EF, right? So then this together means DE over EF is equal to GE over EF. But they have the same denominator, right? So this tells you DE is equal to GE. Okay. Now let me circle this. So DE is all equal to GE. So DE is equal to GE. Okay. Now let's see. So you can do the same thing, right? Check. I'm going to skip a sum step here. So by similar reason, we can also show DF equals GF. Just compare other sides, right? So I want to say that I skip some steps here. I would let you do it as exercise. You should try to do it yourself. This shouldn't be too hard. You just use the other, right? So instead of AB over BC, try BC over CA, right? Or something, the other one, okay? So now you have this, right? Now we can have create some congruent triangle. Okay, so we have DF over equals GF. Okay, so now you can see that we have some like information about DEF and EFG. So now, since we have DE equals GE from earlier, and here DFGF as exercise, and we also have EF as a common side. So triangle DEF should be congruent to triangle GEF by SSS. And I want to emphasize this is congruent scheme, right? And if they're congruent, then that's better because then they have all the angles to be equal. So I would say GF are equiangular, right? All the angles are equal, right? But we also prove that ABC and GF are similar. So we just proved ABC and GF are similar. And for similar triangle, they are equiangular as well. So then you can pass on the equality, right? So the angles would be equal. Right, so we have this. Okay, So then that's it, right? So we essentially done, right? So essentially, the conclusion is you have DEF and GF, they're congruent triangles, so they have the corresponding angle to be equal. But we also have triangle ABC and GF are similar, right? So they're equiangular. So then both of them are having the same angles. Then our goal is actually to compare DEF and ABC at the end, right? So ABC and DEF are equiangular. So let me make this and DEF are equiangular. And that's the goal, right? We start from some sides are in ratio, right? The same ratio. Then eventually we want to prove they are equiangular. Okay, so this is the essentially the SSS similarity scheme. So to end this first part of the video, I just want to go mention the statement of SAS similarity scheme, but I'm not going to prove it. I'll because I already spent a lot of time on proving these two earlier similarity scheme. So SAS says if two triangles have one angle equal to another, and the sides which subtend these angles, or essentially the sides between these angles are in proportional, then the triangles will be equiangular, meaning they're going to be similar. Okay, so let's see. So so if they're equiangular, right, then all the angles are equal, right? Then from AA again, it's going to be similar. So it's like two steps, right? So this tells you if you have two triangle ABCDEF like this, if you have one angle A and D to be equal, and you have the side which subtend this angle will be in proportional, right? This is two assumptions. So AB over AC is equal to D over DF, right? Then you actually prove the remaining two angles are corresponding equal. Then you essentially get back to AAA triangular, similarity scheme, right? So then this will also eventually implies these two triangles are similar, right? Okay, so I will just write here, read textbook proof as exercise. Okay, so I'm going to end this first part video here, then I will continue with the chapter 10, okay?